Okay, so let's build this data path incrementally, but again you need to pay attention to the details. So first try yourself. We have already discussed this. These are the 3 components which you need to build up an instruction fetch data path. So put them in the right order, wire them correctly to build the same thing which we have just discussed. How to fetch the instruction and increment it by 4. Try drawing it on your own notebook. All right. Although I have already shown you, it appears that most of you were sleeping with your eyes wide open. I just asked you to draw the same thing again. Let me show you where it is. I have already shown you here, this part. And this is what we're trying to do. Okay? Yeah. All the slides are posted already. Okay? So what do we have here is the instruction memory. Okay? It's just like you can consider it as a drawers. Where do you want to read the data from? You need to provide the drawers number. You need to provide the address of the instruction. Okay? And the address is stored in program counter. So if you assume that the address, current address is 100, for example. Okay? So the address 100 is provided here. And whatever the value, the instruction is placed at that 100 address will be placed at the output of the instruction memory. Okay? Now, this is a different story how to execute this instruction. But once this is address is calculated, address is provided, it has to calculate the address of the next instruction. And the address of the next instruction is calculated like this. This is the current address plus 4 will help us calculate the address of the next instruction. Why 4? Because we assume that every instruction is 4 bytes wide. Okay? Any question? Isn't it simple to draw? So it's again, PC is a 32-bit register, and we need to increment by 4 to execute the next instruction, which is in order. Okay? So this was the instruction fetch part. Let's go to the R format instruction part. And we are actually maintaining the log of components that we have already used, or some of the components we might need to use again by looking at this log shown at the right of your screen. Okay? So in the R format instruction, we need to read 2 registers operand, perform arithmetic and logical operations, and write the register's result back into the register file. What components do you think we should be using here? We have already seen this. R-type instruction, yes?
We should be using the ALU for this.
ALU for performing addition. But where do you get the contents from? The contents on which we need to perform the addition.
From the immediate.
No. No. Hold on. Yeah? Yep. Register file. So register file contains all the registers data. Okay? As it says, the R format instruction, it is clearly shown up here. Read 2 register operands. So where do you read the operands from? From the register file. So we need to implement the R-type data path. We need a register file and the ALU. Okay? So again, let's put these 2 components in the data path components and talk about the load and store instruction. So in load and store instruction, again we need to read memory in load instruction and update the register. In the store instruction, we need to write the data into register. So in both cases, we need to read register operands. So when we talk about reading register operand, which means that what component is required? Register file. Okay, where do you read the registers from? From the register file, okay, which is already present here. So we are talking about using the unique components here. So calculate the address using 12-bit offset. So what do you think? The 12-bit offset and to write the data or read the data from memory, what 2 additional components we need apart from the component shown up here on the right?
Is that immediate generator?
Immediate generator and the main component for memory instructions. Where do you read the data from, or where do you write the data to? No, I mean in LW instruction, where do you read the data from? Or in store instruction, where do you write the data to? In memory. Okay, so you need a memory, data memory, as well as immediate generator component. Why do we need immediate generator? To extract the 12-bit immediate data and sign extend it to 32-bit value. Okay. So we have these 2 components also. And what about the branch instruction? Do we need any additional component here? So in branch instruction, we can fetch the instruction from instruction memory. We can read the register content from the register file. We can perform the subtraction, BEQ in case of BEQ, using ALU. What do we need to do next? We can also extend the 12-bit data using the 12-bit immediate generator. What else do you see in this? AND gate? Yeah, AND gate will be there, but what happens to the 12-bit data in the case of branch instructions? So let me recall here, it's a typical format in branch instruction where the placement of bits is a little bit different than the other formats. You remember we did not encode the rightmost bit, 0th bit. Why? Because we assume that the instructions are always either 4 bytes wide or the 2 bytes wide. So that's why this value will always be 0. Again, forget about this. This is the format for 12 bits data. So what happens when we reconstruct the immediate data? What we do? We shift it left to add the dropped 0 that we initially dropped. So remember this question in your exam? You were supposed to be placing the 12-bit, arranging the 12-bit into appropriate location. So this is the 11th bit which goes here. This is the 12-bit. So after constructing this 12-bit value, you need to actually append or add the 0 on the right. How do you add a 0? By shifting the entire value towards left, right? So if I have extracted a value, let's say this is 0, 1, 0, 0, 1, 0, for example. Okay, let's say this is a 32-bit value. How can I append the 0 on the right just to retrieve the original value in the branch instruction? By shifting the value towards left. Okay, when I shift the value, it will become 0, 1, 0, 0, 1, 0, everything. So one additional 0 has been added here. Okay, so this is how the branch instruction, the 12-bit immediate value in the branch instruction works. Do you recall this question in exam? So we need shift left thing. So here is, so previously what you were looking at, the entire 32-bit data was giving into this ALU. But it first passed through the immediate generator, which will extract the 12-bit value, and then it has to shift left in case of branch instructions. Okay, and then we perform the addition with the current address of the instruction to calculate the branch target. Okay, and when we perform equal operands, when the operands are equal, the branch target address becomes the new PC, new program counter, and it is set to be branch taken. If the value, if the 0 signal is 0, it means that the branch condition does not satisfy. It will still execute the next instruction in order, which is PC plus 4. Okay. So if you recall this, in the case of branch instruction, we can execute A minus B operation. The 2 register BEQ A, comma B. So we actually perform the subtract operation. If the resultant bits, all 32 bits are 0, they are ORed to produce a one bit value output 0, and then it is passed through the inverter to indicate with the 0 signal. If it is 1, it means that the result is 0, which means that the condition satisfied. Okay. So now we need to compose the elements. So R-type instruction use ALU with inputs coming from 2 registers. Okay, and the value stored in a destination register comes from the ALU. Agreed? Do you guys agree? In the case of a R-type instruction, register instruction, where do the operands come from? Both 2 operands come from the register file. Okay, both operands are registers. So if the instruction is add instruction, RS1, RS2, and RS3. So these both of these 2 values come from the registers. Okay, and the output is also stored in a register. Here in this example, RS1. Okay. What about memory? If it's a memory instruction, let's say LW. So where are these inputs coming from? Let's say the instruction is this LW, S1, offset, and S2. So every instruction pass through the register file, and then the ALU, and then the data memory, and so on. Okay. So first of all, after fetching the instruction, this is ALU. So where are the 2 inputs coming from? Come on, it's in front of you. The first input is coming from the register. Okay, so here the input is coming from the register. Where this input is coming from? From the another register, or it's something else? Is what? The offset value, which is the 12-bit. It must be coming from the immediate generator. Okay, so it will not be coming from the register file. Okay, so it will come through the IMM generator. And again, who will control this? It will be controlled by the multiplexer. And the value stored into a destination register comes from the memory in case of load instruction. Okay, so now let's do this activity to construct the data path for R-type instruction. You need to use only those components which are highlighted, which are just lightened. You do not need to use this, which means that assume that the instruction fetch data path, you do not need to construct it here. Assume that the instruction is coming right into the in this stage, the register file. Let me recall that again. So assume that the instruction comes here, and then you move forward. So just to give you a hint, after assuming that the 32-bit instruction is already available, so assuming that the 32-bit instruction is already available, this is the instruction. So where should it go first? The instruction always have the register contents that we need to read or write. So it will go into register file. Let's say RF, and let's say RS1. You can just simply route it like this. This is RS2. This will go like this, and RD. These fields will remain there. Okay, this is the hardware. You cannot change it according to what type of instruction it is. So even if it is instruction like store word, yes. Even though there is no RD field, but this RD port will always be there in the hardware, of course. Then this is the write data port. Okay. You need to determine where the data in this port will be coming from. It will not be coming from here. Okay. And here, let's say read data 1, read 1, this is read 2. Again, this is 32-bit data, and the next component you should draw which component should be coming next. ALU, yes. But in ALU, if it has an ALU, let's say you draw ALU here like this, one of the input must be coming from the register always, because every instruction, no matter what instruction it is, has RS1. Okay, RS2, some instruction has RS2, some instruction has no RS2, rather an immediate data. Okay, so you should decide this input where, so this one is coming from directly from here. Sorry, where did it go? Yeah, so the one of the input is coming from here directly. This input has to be decided where should it be coming from. It could either be coming from the immediate generator or from the another register. So how do you put it in place? Draw it on your sheet. Okay, so first of all, if it is add instruction, add RS1, RS2, RS3. So both RS1 and RS2 are the registers. The data RS1 will be coming from here, RS2 will be coming from here directly, right? But if it is another instruction, let's say LW, let's say RS1 offset. Sorry, this is not RS1, this is let's say some register S1, and this is S2. So here, this is actually the source register 1, which comes from here. Where does this offset come from? It comes through the immediate generator, right? So you need to have immediate generator value, which takes the 32-bit input instruction, extract the 12-bit immediate value, and generate the 32-bit extended immediate value. Okay, and then it should go into here. Who will select? A mux. The mux will select whether the second input of this ALU, where should it be coming from? Either from this path, either from this path, or this path. Okay, so this mux signal, there will be a control signal which will decide where to provide this second input to ALU from the immediate data or from this one. So once you have the ALU, this is the 32-bit data. Okay, now this 32-bit data, in case of add instruction, what it should be doing? In case of add instruction, what should it be doing? What does it do in add instruction? It performs the addition operation and then write the results back into registers. So it means that this thing should be coming here to WD port, write data. Okay, but this is not complete thing. If it is LW instruction, what does ALU do? In LW instruction, ALU calculates the address of the memory. Where do we want to read the data from? So this one is DM, which stands for data memory. This is the address port, this is the write data port, and let's say this is the read data port. So in case of LW instruction, it will provide the address here. Okay, the data that is read from memory, where should it be written? To the register S1, right? So which means that the data is coming from here also. And when we have two different sources of data and we need to connect the one of the inputs to the output, what should we be doing?
Mux.
It's a mux. Okay, so there is also a mux here, the second mux, which will decide who will be writing the data back into registers here. Either it's an add instruction coming from the ALU, or it's an LW instruction coming from memory. Get it? Yes?
For IMM, what were you saying it does before and after it gets the 32-bit?
So it takes the 32-bit instruction, okay? It extracts the 12-bit immediate value from the instruction and sign extend it to 32-bit. So now this 32-bit is the immediate data. Okay? What about the store instruction? If we have this store instruction, what do we do in this store instruction? Let's write its store instruction here, SW, let's say S1, offset, and S2. Okay? What do we have? This is the RS1, okay, which will be coming from here. This is the offset that is coming from here. So it means that the ALU will be calculating the address which we will provide here. So what happens in the store word instruction? At the provided address, what do we do? In case of a store, we store the data, write the data into memory. So we have to write the data into memory. Where this data is coming from?
The address.
No, the address signifies where do we want to write.
Oh no, the actual data.
So the actual data that we want to write is coming from the register, S1. So this is this register. It is coming from here.
Okay. So
okay.
Just to clarify, so RS1 is our address, and RS2 is the actual data that we're storing, right?
Here, yes. Okay. Understand? So you can assume that all these wires will always have some data available to it. It will always be providing some data to it, but depending on the instruction type, if it is SW, so mem write signal will be active. Okay? It will indicate that this particular instruction is writing the data into memory. Okay? Let me quickly show you the actual diagram. You can take a picture of it, the solution. So this is the actual picture.